So now we want to focus on the radiation between two surfaces. What we've done so far was the net radiation from surface I. And we said that we can write it as a difference between the potential of the black body radiation and radiosity, and then we divided that by what we call the resistance on the surface. Now we want to see what else would impact the radiation from one surface to a specific other surface, or between two surfaces. So this is what we call the radiation from 1 to 2. This is more like what we did for black body radiation before, and what we were trying to calculate for black body radiation. We said radiation exchange between two surfaces is the radiation leaving the entire surface 1 that strikes surface 2 minus radiation leaving the entire surface 2 that strikes surface 1. So we're going to now do the same as what we did with the black body, except that the black body case was a very easy one because it was black body and the formulas are easy. There's no reflection. So all of those assumptions were there. Now we want to do the same. Instead, this time we're thinking about the fact that the surfaces are actually not black body. So now I'm writing my radiosity J1. I'm including J1 in my relations because before in the black body relations, I said that radiosity is actually equal to my emissions. Now I just use the radiosity because it could be your emission from the surface, or it could be part of the irradiation that's reflected. That's altogether radiosity. So now my relations are changed a little bit. I write the radiation from 1 to 2 as A1J1, and I multiply that by the view factor from 1 to 2, minus what the radiation leaving the surface 2 that strikes surface 1 is. So that would be A2J2 that's leaving surface 2. The part of it that actually strikes surface 1 would be why I would multiply that by F21. The reason I have F12 and F21 is I'm only looking at the portion of radiation from 1 that strikes 2 and the portion from 2 that strikes 1, because I'm specifically looking at the net radiation between 1 and 2. So now I know that I can write, instead of A2 F21, I can write F1 to A1. This is from the view factor rules that we discussed last time. And now I can just factorize and make it look nicer. A1 F1 to J1 minus J2, or I could have written A2 F21 J1 minus J2. And now I arrive at this relation. I say that the A1 F1 2, I'll bring it to the denominator. Well, of course, you'd have to do 1 divided by A1 F1 2. But I bring it to the denominator, and the reason I do that is just to get what I call a space geometrical resistance to radiation. I call it space geometrical resistance because it's a factor that only depends on the geometrical characteristics of my space. So depending on how the two surfaces view each other and how your view factors are, this R value would be defined. But we're basically making this look this way in order to make everything look like the previous slide. A potential difference divided by a resistance. Going back all the way to our use of circuit analysis, we'd like to use a potential difference divided by a resistance because then later our analysis will be easier. So in the same way, we can use potential difference here between, for example, Ji and Jj if our surfaces were surface I and surface J. You would have between the two radiosities, you would have this resistance that only depends on the way they view each other. This has nothing to do with the type of your surface and its emissivity and reflectivity and all of that. This is specifically how the two surfaces view each other. The resistance that does depend on the emissivity and reflectivity and all of that, that's this other resistance that we discussed in the previous slide. And this other resistance that we discussed in the previous slide. These two resistances that I'm putting a star next to, these are your surface resistances, and that depends on the type of surface that you have and how it's different from a black body surface. That resistance, it's different. It depends on the surface type. But then the resistance that we're defining as the space geometrical resistance here, this only depends on how the two surfaces view each other. Now, if I wanted to see how the relations would look like if I had black body, I can write everything using my J values as black body, because radiosity in black body becomes emission of the black body. So then I'd be able to write, for example, the radiation from 1 to 2, the net radiation from 1 to 2 would be A1 instead of J. Now I have EB1 F12 minus A1 EB2 F12. And then I'd be able to write, instead of the EB1, I'd be able to use the Stefan-Boltzmann constant and temperature to the power of 4, and this is what I would have. So for a black body, I would have in between the two emission values, I would have again this resistance. If you remember from the radiation exchange for black body, this was the relation that we used. This relation here was what we used actually in the example, and we said that it's very easy to deal with analysis of radiation when it's a black body analysis, because you only have one resistance in between your surfaces. The surfaces don't have resistance. You only have one resistance, and that's your view factor resistance or space geometrical resistance. So with the case of black body, we're only discussing this part of the circuit. So you only have your radiosity becomes equal to your EB, and this one becomes equal to your EB emission from surface J, and then you only have one resistance in between, which is only dependent on how the two surfaces are oriented. In the case of having an actual surface, which is not black body, this circuit expands to having two more surface resistances. So now we want to see what the net radiation between more than just two surfaces is. So far we've seen net radiation from surface 1 to 2. What if we have a third surface and a fourth surface and a fifth one and an nth one? So if your surface 1 views many other surfaces, in order to calculate the net radiation from surface 1 to all those other surfaces, you can just add up the relation that we came up with in the last slide for all those surfaces. In other words, there's this summation here for surface 1 to 1, 2, 3, 4, all those surfaces all the way up to n, and your values are AI is from surface I, Fij, which is, let's say, surface 1, F1j, and then J1 minus Jj, which is your other surface. So in order to do that, you just add up all the radiation from surface 1 to those other surfaces. Depending on their view factors, you'll be able to calculate the net radiation from surface 1 to all other surfaces. Now, I can make this equal to the net radiation that goes off of surface 1. We already calculated the net radiation from surface 1 2 slides ago as well, and that was in terms of the type of the surface. So I said that the net radiation from surface 1 depends on the difference between the black body emission and the radiosity of surface 1. We already said that, and we already came up with the surface resistance for that we said it depends on emissivity. We can also say that, well, the net radiation depends on also the way the surface 1 views other surfaces, and that would be many surfaces, whatever it can see. So that's Ji minus Jj, and we said that these J's are depending, like they go from 1 all the way to the surface n. So surface 1 to 2, 1 to 3, 1 to 4, 1 to 5, all those surfaces. So we make them equal because they are both representing the net radiation from surface 1. And then we generally like to represent this in a circuit form like this. So we say that the net radiation from surface I is this Qi. Now, from EBI node to Ji node, there's this resistance for the surface that we already came up with, and that's the left-hand side of this relation. Now, from Ji, your net radiation could be split into the different surfaces that it views. So depending on the view factors, some of it goes here to surface I1 or surface 1. Some of it goes to surface 2, some of it goes to surface 3, some of it goes to this n-1 surface, some of this goes to surface n. So depending on your view factor, your net radiation from surface I is split into all these different smaller currents. But the total current, or the net radiation from surface 1, is the one that you see here. So you can calculate the net current by picking these two node values and dividing them, well, the difference between those two node values, and dividing them by the resistance here. Or you can calculate your net radiation by just adding up all these Q values that you can calculate. Now these at some point will meet some J1 point. So for example, Ji and J1, there's a difference, and you divide that by this resistance, you should be able to calculate what your QI1 is. There's also again Ji and J2. The difference between these two divided by their resistance is going to be this Ki2. Again, the difference between your Ji and this J3 is going to be your Qi3, and so on and so forth. We are going to look at an example to work with a circuit and see how we form a circuit for a radiation problem.